Okay, welcome back Physics 20s to our next lesson. This is 1.7 and we're going to be looking at the acceleration of gravity. So let's imagine that you take a mass that's quite heavy, something like 20 kilograms, and then you take a sheet of paper and you decide to drop both of them. You probably already know that gravity is going to pull both of these objects to the ground. What I want you to consider is which one is going to hit the ground first. And let's say you do an experiment and you drop them, and this is what happens. The 20 kilogram falls and the paper kind of swings and hits the ground second. Because it takes longer for the paper to fall and the paper is a lot lighter, you might conclude that gravity pulls heavier objects towards the ground at a higher acceleration. However, if you take that same sheet of paper and just crumple it up and then you drop them both, the paper has not changed its mass, but now they're going to hit close to the same time. Maybe not quite, depending on how much you've balled it up, but it is going to change it. So this means that the acceleration of the paper wasn't limited by its mass, but it was limited by the air resistance. So what if you could get rid of all of the air? So I'm going to take this next example. We have all these three objects, the crumpled paper, regular paper, and mass, and we're going to get rid of all the air. If you could do that, they would all fall at the exact same rate towards the ground, because gravity accelerates all masses towards the center of the earth at 9.81 meters per second squared. This has actually been shown in in a YouTube video where they actually take this chamber and suck out all the air and drop objects. So what we conclude or use from gravity is that all masses of relatively low mass near the Earth's surface accelerate towards the Earth at 9.81 meters per second squared. So two things that I had to put in there was relatively low mass, which means significantly less mass than the Earth, because then you get into some complications if you're dropping something really heavy, and also near the Earth's surface. As you go farther away from Earth, the amount of gravity the acceleration of gravity will decrease. But for all these examples in chapter 1, we're going to be using 9.81. Generally, we consider up to be positive and down to be negative, so we're going to call gravity negative 9.81 meters per second squared. Now, I'd like you to try this. Using your knowledge of kinematic equations, the four that we've already looked at, determine the displacement and velocity of a launched object at each given time. So we shoot a ball up, and as soon as it launches, 0 seconds, it's considered to be at 0, wherever that's launching from, and it's going at 20 meters per second. So I want you to try and fill out the rest of the chart for where is it at 1 second, 2, 3, and 4 seconds, and how fast is it going to be going at 1, 2, 3, and 4 seconds. Okay, so here are the answers. What I'm hoping you did off the start was list your variables, VI, VF, A, T, and D. I found that we don't have displacement, we don't have velocity. The equation to solve for displacement is right here. It's the one without VF. And the equation to solve for VF without displacement is right there. Use those to fill in these columns, and these were the numbers that I got. So it starts at 0 meters, then it goes up to 15.095, so it's pretty high. But then it doesn't go up as much the next time, only 20. Then it goes back down to 15, and then it's almost at the ground at 1.5. This kind of makes sense. If you shoot a ball up, it's going to slow down, and then it's going to come back down towards the ground. Its velocity is pretty high off the start in the first second, but then it slows down to almost stopped when it's all the way up 20.38 meters in the air. And then the velocity becomes negative as it starts falling downwards and becomes quite negative just before it hits the ground when it's 1.52 meters above the ground. So we haven't looked at graphing yet, but we want to consider what this would look like on a graph if we had the position here and the time down here. We saw the displacement went up in big intervals off the start, then small, and then went back down. It would look something like this, which shows a curve. Now, back in Science 10, you looked at graphs of D versus T. We're going to look at them again in the next couple lessons. But just to remind you of this, the rate or the slope is equal to the rise or the change in our displacement over the run, which is our change in time. And we already looked at change in position or change in displacement over change in time, and that was equal to velocity. So the slope of this is going to represent the velocity. And we can see at the start here, it's a steep slope going up, probably about 20 meters per second, because that's what we started off with as our initial velocity. And at the end, it's coming down really quickly. Now, the thing that's important about this graph is it is completely symmetrical. So the speed that it's going up at is the speed that it's going to be going down at, 20 meters per second. But the velocity that's going to be going down at is negative because we have to include the direction there. So it starts going up at 20 meters per second, falls back down at negative 20. Also, like at this point here, if this was, say, something like 10 meters per second, at the same position over here on the x-axis, it's going to be at negative 10 meters per second on the other side. So it's completely symmetrical. And then we can cut this right in half and have it equal on each half. What that tells us is that the time here, so I'll put time to go up, which is that whole section it's going up, is equal to the same time it's going to take to go down. So if you shoot something up in the air, it's in the air for 10 seconds, it took 5 seconds to go up and 5 seconds to go back down. So that is also useful. The other useful thing is right at the top here, the slope is 0. It goes completely flat. And we said from over here, slope is equal to the velocity. So the velocity right at this point is equal to 0. Now, what is important about this point is if we look down here, it's exactly half the time that it was in the air. So if you throw a ball up and it's in the air for 10 seconds, you know at 5 seconds it stops. This is good because this can give us a reference for calculating those kinematic equations. When we saw our variables of VI, VF, T, and D, that can give us information about the velocity at that point. This also, with the time up and time down, can give us information about the time and the relationship between VI and VF. If we look at when it left and when it lands, that'll give us information that they are the same. So lots of things that we can get from this symmetrical graph. So these are the conclusions: that G, or gravity, is equal to 9.81 meters per second squared. That's constant. We usually put a negative in there because we talk about that being downwards. The time spent going up is equal to the time spent going down. And at its highest point, at its maximum height, the vertical velocity is going to be 0, and that's half the time. I'll put that in there as well. Half time of trip. For the trip, it goes up and down. So now let's try some practice questions. It says, if you shot a tennis ball into the air at 14 meters per second, what would the velocity be when it hits the ground? How long until it reaches maximum height? And what would be its maximum height? Let's start with the first one here. I'll switch to something we can see a bit better. Let's go with bright green here. What velocity would it hit the ground? Well, we know from that graph, if I go back to here, that the velocity that it goes up with is the same as the velocity that it goes down with, except for it's just switched directions. So let's go back to that question, and it's really easy. All we have to put in is negative 14 meters per second for our answer there. Next one, how long until it reaches its maximum height? Okay, this is a little bit trickier. I'm gonna switch to red here. I'm gonna list my variables, VI, VF, A, T, and D. And I know that the initial launch is 14 meters per second. Now I know that the VF is negative 14, but this is asking about its maximum height. Its maximum height is not when it hits the ground again, so not when its ending velocity is negative 14. What would its final velocity be when it's at its maximum height? It would be 0, right? That's the very, very top. At its maximum height, it's going 0. It goes 14 meters per second up to stopped, and right then it's at its maximum height. So I can put 0 meters per second there. My acceleration, I know, is negative 9.81 meters per second squared. The time, that's what I'm looking for. And the displacement, I don't know that either. But the first one's looking for the time, so I'm looking for the one without D. This is A is equal to VF minus VI over T, and we're trying to solve for time. So my time is equal to my VF minus my VI over A, and that is equal to my final velocity of 0, my initial velocity of 14 meters per second, and the acceleration of negative 9.81 meters per second squared. And when I put those in my calculator, I'm getting an answer of 1.427 seconds. If this was my final answer, I would have to round to 1.4 seconds as that answer. Now, lastly, for the maximum height, I still am going to use these variables, except I want to solve for the displacement. So then I want the equation that does not have time. That is VF squared is equal to VI squared plus 2A and D. I'm trying to solve for D. So first I'm going to minus VI, like that, and then I'm going to to get displacement, I just have to divide by 2a, and I should get my displacement. So let's fill in those values. VF was 0 squared minus my 14 meters per second squared divided by 2 times negative 9.81 meters per second squared. And I get an answer of 9.9898. So that would round up to 10 meters for our answer there. So this knowledge about gravity and about that symmetrical graph is really useful for solving questions that involve things going up and going down, which you call projectile questions. So hopefully that gave you an understanding of that concept with the graph and some examples here. Use that to try your practice questions. Ask me any questions in the live time, and I'll see you in the next video.